Okay, good morning. Before I start, the announcement I'd like to make. There's no quiz for this week, okay? So focus on studying for your term test. Now, term test 2, I've finished setting the question. I've also have posted the formula sheet on Avenue to Learn that I make an announcement. So please review with the formula sheet, okay? It's enough for you to do your questions. Term test 2 will be, I still have students asking me what homework they should focus on. Homework 5, 6, and 8. Okay. So those are the homework that you should be focusing on. And today's agenda is more like a review. Okay. The first part, I'm going to review 2 examples on unsymmetrical shear from homework 6, question 4, and question 6.68. Why I do this too? Because I have questions from students asking me about these 2 problems. And then I will go into an example of shaft under combined loading. Okay, so this is still nothing new, but something that will help you in your term test. Okay, so we are more important. I want to highlight about the shear stress consideration when you're dealing with a shaft. Okay, so that's what I'll be doing today. So on Friday, I could not attempt this problem because of time. Okay, so I have students asking me about this part, okay, of the problem. So what you see over here, if I zoom it close enough, you'll see that the solution is based on the frame of reference at the bottom. Okay. And yeah, you realize that once you start solving problems like this, different method does evolve, but it's not the same technique as I taught you guys, right? What we say in this thin wall analysis, the first moment of area cannot cross the centroid. By doing things like that, we're breaking one of the major rules. Okay, because I believe some of these solutions are done by the publisher who employ a mathematician rather than an engineer. Okay, so the answer is still correct, but the approach is different. So I'm going to use the same method that I teach in class, okay, to solve this problem. Okay, so what I will not do is I will not find I at all. Okay, second moment of area is straightforward. But I'll start by looking at the area and by applying what I taught you. Okay. So our approach is still the same. We are going to look at the right flange. Okay. So we don't need to use the left flange because we need to find a point to calculate the shear center. Okay, so this is the point that's considered. So there's no point finding what is going on the the force on the left flange, because it's coming directly at point at the dot over there, and there's 0 moment. So that's where we concentrate on the right flange for that reason only. Okay, so when we consider the right flange, I'm going to apply exactly what I've taught you. Okay, as I said, the solution by the publisher, the method is not exactly the same, but that's where I want you to try. Okay, I want you to try what I've taught you and to gain the confidence. So this over here that I've just drawn is our centroid. Okay. And we know the distance from here over here to here we will call it H2 over 2. Okay, and then the distance from here to here is our y. Okay, so this is the area that I want to consider. Okay, that is the area I want to consider. So to calculate the area, okay, area of the shaded region, so is equal to area is equal to the thickness we are given, the thickness over here is equal to T2. Okay, so T2 multiplied by H2 over 2 minus by Y. Okay. Then we are going to find our first moment of area. Okay. And I did not see, if we call the axis over here, this is our X, this is our Y, or let's do the normal form because it's cross section. I'm going to call this QZ. Okay. So the first moment of area is equal to about the z-axis is equal to A and Y bar. Okay. So where is Y bar is the distance from here to here. Okay. So this will be equal to T over 2 H2 over 2 minus Y. Okay, so that's a width and depth, that's the area. Then is H, oh, my H2 is like H squared, have to be careful. H2 over 2 minus Y. Then is H2 over 2 plus by Y multiplied by half. Okay. Then we tidy things up a bit. So this is equal to T2 over 2 multiplied by H2 squared over 4 minus by Y squared. So if you look at the solution where we are, we're at QZ, okay? Our form we come out is very similar, right? The form, yeah, look at the solution manual is very, very similar, okay? So next, we want to determine the shear stress. Okay? So shear stress is equal to VQ over IT. Okay? I don't know, we will not substitute our, I mean, V and I are constant, T we just need to know, right? So when we substitute into that, we have V over I. Now the T becomes T2, right? Then multiply by T2 over 2 H2 squared over 4 minus by Y squared. So we realize that we can get rid of our T2s. So this will be equal to V over 2I, right? So I brought, so you have H2 squared over 4 minus by Y squared. Next, we are going to find our force. So we integrate in a limits of H 0 to H2 over 2. Okay. Okay. And then the shear stress multiplied by the change of the cross-sectional area, right? So when you do this, we get, you integrate 0 h2 over 2 v over 2I h2 squared over 4 minus by y squared. The thickness, the cross-sectional area, the thickness is a constant. The change is in the y. So now we tidy everything up. Okay, so it's v multiplied by, sorry, this is T2 over 2I. Okay, then we just integrate the term inside there. 0 h2 squared over 2. And then all we need to do is just to integrate the term h2 squared over 4 minus by y squared dy. Okay, so very simple integration over here. So you get h2 squared y over 4 minus by y cubed over 3. 0 to h2 over 2. I don't know why I put a squared over here. Silly me. So finally, we just substitute v over 2I. So this is equal to 2 cubed over 8. So this is h2 cubed over 2 to the power 3 is 8. 8 times 6 is 24. So finally, v t2 over 2I, right? So this will be, so you times 3 over here, times 3. This 2 over 24 is 1 over 12, right? h2 cubed over 12, right? So this is the force for the top half. Right? Why top half is because the limit is from 0 and we go to h2 over 2, right? So to consider the full left flank force, all we need to do is we need to multiply by 2, vt2 over 2 multiplied by h2 cubed over 12, and I'm missing an I over here. Okay, so this will be equal to vt2 over I h2 hold on. Let me check the answers first, okay? Can you hear me online? Can someone say yes, please?
Yes.
Okay, I was never cut off, right?
No.
Okay, thank you. I thought I got cut off. Okay. So you see that the answer is exactly the same. Okay, so as I said, mathematically, I'm not saying that they are wrong. They just take their reference at the bottom. But if you're going to apply the rules that I've taught you, that the first moment of area cannot cross the centroid, then mathematically that is wrong. I mean, mathematically that's not valid, okay? So this, just apply what I exactly teach you, because the highlighted region, as you can see, is VT2 H cubed 2 divided by 12I, and we get exactly the same thing, but our approach is just slightly different. Okay, so student asked me about, hey, can we just cross the centroid like this? My answer is no. It's different when it is longitudinal shear. Okay, longitudinal shear, it has to fill up the member first. Okay, then it's okay to let the first moment of area cross the centroid. For this case, no. Okay, very important to know that. Okay, so this is one example. Then any questions from any